Yo, what's up, what's up? Welcome back. Today we're working on my operating system. It's an operating system that I've developed on stream or with videos on YouTube, and it's a attempt to learn how operating systems work, build an intuition about what's going on under the hood when we write applications on a normal operating system. And so we've gotten kind of far. We've got like an x86 operating system. It's written in Rust, and it's currently got like, it's starting to resemble a real operating system. We have like input, we have graphics, we have internet, so we have like PCI, Ethernet, ARP, UDP, TCP. We've like written a web server, we've written a game. We have like the basics like memory allocation and logging, some form of concurrency through Rust's async await model. And what we're working on right now is we're trying to prepare for multi-core support. So right now what happens is our operating system boots, and it only initializes on one CPU. And our like way of doing multiple things at a time is by using Rust's built-in async mechanism, which is basically like it's a thing that you give it a thing and you say like check this every once in a while, and you make up rules for when you should check. And you can like write functions that look kind of like normal functions that will like convert into this thing that you pull. And then we package all of our different things that we want to do at once as like different things that you want to check. You put them all together into like one thing to check, and we run that. And that's great, except that all works on one CPU. So the way it kind of looks, just to draw that out, is like you have like one unit of work, and inside him he has like other units of work. And what happens is we like check this, and then after that we'll check, but like by checking this, he'll kind of like check this, check this, check this, and each of these guys has like units of work inside, etc. So that all happens on like one core. And what happens is like when you do like IO or something, he basically just says, hey, I'm gonna wait for something, like I'm waiting for a packet to come in the Ethernet from the Ethernet card. So I've got nothing to do right now, just move on. And so like when he says that, the CPU then goes like, all right, I'll do something else then, and I'll go work on to like move on to one of these other units of work. So that's all working, but we don't have any like real parallelism. So since we only have one core, we're only really doing one thing at a time. And what we want to do is we want to do multiple things at a time. We want to eventually initialize all 4 CPUs, or all n CPUs. I guess we don't know how many they're going to be. And we want to see, we want to make sure that we're like ready for that. So the current implementation, let me just make sure that I can run this right now. Hold on, let me just quickly set up some system stuff that's needed to get this to work right. So let me just, I've basically got to like set up the internet for this guy. He's got like a host internet card that he needs to integrate with. So let me just make sure that I've got that guy set up right, and run. Cool. So our OS boots. It's kind of slow in debug mode, so if I run and release, it's kind of more usable. We see like logs, we see the game running, etc. So let's see, what were we saying? Right now there's a lot of assumptions about single threadedness. So if we look at like an example from last stream that we fixed, is the logger. So if I go back a commit and we look at the logger, our logger implements, hold on. I thought it did. This is a bad example actually. Hold on. Let's see. Okay, here we go. So an example here is this printer, or maybe this guy's a better example. Yeah, okay. So this, there's a thing that we stick in static memory, this like exit handle. The idea is that we want to be able to call like just a free function exit that will like shut down the OS and like propagate an exit code to the parent OS. And internally, he's using a like ref cell, which is like a way to it has this like API on it that says like I want to use this as like I want to lock this essentially, but it's not really a lock. It says like I expect to be the only user of this thing, and if he's not, then he crashes the OS. Great. But internally, he uses some like non-thread safe counters. He just has like a normal integer in there that he increments, and he says like, oh, if I'm using this, I'll increment this integer, and when somebody else uses it, they should check if that integer is incremented. And that works great on a single thread, but once you have like multiple cores in the mix, you need to like have some like synchronization between those guys. And so what we do is we've said like, hey, we're using this type. We know it's not a synchronized type, but we know that we need to worry about it. And we've kind of like made this assumption all over the OS. So what I want to do is I want to start like looking through where we've made that assumption and start like fixing them a little bit with like some atomics and stuff. And then I want to fix our future executor. Our future executor also assumes that it's going to be the only executor running and that nobody else is touching him, or that nobody else is running it at the same time. And that means that like there are some assumptions about using like static memory to store stuff and like to make propagation to interrupt handlers and stuff easier. And we kind of have to fix that up too. So that's what we're working on today. And I think what I'll probably do, I'll start looking through these sync implementation firsts and start like evaluating them one by one, trying to figure them out. And from there, we'll probably move on to fixing the future thing. Yeah. So I think probably the first thing that I want to do is I want to fix, I know that my mutex, which is like kind of funny, that my mutex type is not thread safe. And so that's probably the first thing to fix. Once we have that down, then we can kind of start working through, other cases. Like we can start using our mutex and our lock-free queues and stuff to start implementing fixes for the other stuff. So let me just go back to latest and greatest, and let's start looking at an async mutex, or fixing the mutex. And this is 740. Okay. So our mutex type, he's pretty straightforward. In the world of async code, basically all we do is we have this like is lock free, and we check like how many people are trying to use this guy. And if there are any users of him, then he's not free. And if there are no users of him, then we can take him. And so what happens here is, since we're only in a single thread, we don't have to worry about like multiple people trying to increment the count at once. All we do is we say, can I get him? And if I can get him, then I get him. Like easy, I'll increment the count and return my like mutable guard. And so what we need to do is we need to make this like a thread safe thing. So let's see. So we need to think about like what happens when multiple people try to lock at the same time. And also, we need to think about like, well, this count isn't really valid between multiple threads because it's not going to get synchronized automatically. And so what we actually want to do here probably is the first obvious thing is to convert this into like an atomic usize. Right? Because that will force the synchronization between threads. Which means I need sync atomic usize, and to use the usize, we're gonna need ordering, which tells the compiler what order, like how strict do I need to be about these atomics, essentially. So this guy, he goes 0 into, great. Let's think about this now. So this guy, when we lock, we wait until we think we're able to lock him, and then we try to acquire. And now if like multiple people are locking at the same time, there's a chance that could fail. So this should go into a loop, and we can say if we successfully acquire the lock, maybe we say if let sum guard is equal to acquire, then we return guard, else we can keep going. That seems reasonable. Now let's think about what else is happening here. So this mutex locker, he needs to take an atomic use size now. He needs to check if it's ready. So here he's going to load. So let count is equal to self.count.load, and he's going to take in an ordering, and he's going to make sure that he's using acquire ordering, I believe. When coupled with the load, if the loaded value is written by a store operation with release or stronger ordering, then all subsequent operations become ordered after that store. In particular, all subsequent loads will see data written before the store. Great. And here we pass in the count now. And that's all we need to do for this like check for if it's ready, right? We're going to try to acquire the lock again later, but if we don't acquire it, like that's fine. So now we need to make this self.acquire. So this guy's going to return an option, right? Because he might fail now. He might not be able to acquire the lock. And here we're going to do some sort of like, compare exchange week. So he's going to like try to get the value. So he's going to say let count is equal to self.count.load with ordering acquire. And here he's going to check the count again. So he's going to say if count is not equal to 0, he's going to return none. He failed. Great. He's going to try to increment the count by 1, and he's going to try to put that back in. And so now we're going to say self.compare, or not self, self.count compare exchange week. The current value is count. The new value is count plus 1. And I think that this guy takes in 2 orderings. He takes in success ordering and failure ordering. So success describes the required ordering for the read, modify, write operation that takes place if comparison with current succeeds. So I think we put acquire and release because it's a read, modify, write. And failure describes the required ordering for the load operation that takes place when the comparison fails. So this is, I think it's, you do like ordering acrel and, acrel and ordering acquire here. And here we say if this fails, we return none. Because somebody else got the lock before us. Now at this point, we should be guaranteed that only one thread makes it through. Right? I'm pretty sure. And so if we're the only person that made it through, we can just return our mutex guard. So the count is going to be our atomic count. And inner is going to be the same thing. The value is going to be what we saw before. So now I have a problem here where this guy thinks he was a mutable use size, but he should be an atomic use size now because it's for multiple threads. And when we free the mutex, we should be damned sure that we're the only guy that has him. So we can just say self count store 0 ordering release. Great. Great. We're now struggling because we cannot apply equals automatically for the count. So where am I even using this equals? I think nowhere. I shouldn't ever be comparing the mutex guard directly. So I think that's fine. And here we need to say that we succeeded in acquiring the mutex. Great. Here, when we try lock, we can probably just call self.acquire. There's no other things to be done here because now the self-acquire can fail when the mutex is not available. And just fixing a couple like lifetime things and like references. Great. And maybe that's good now. Maybe that's good. Cargo test to make sure that our tests for our mutex still pass. Great. Great. So that's this guy. He should still pass. Test try async lock. That did in fact run and still passes. And I think now our implementation is safe. Now, I did see something while I was browsing atomic docs today that I wanted to like think about a little harder. So I saw that there's this like atomic fence. And I don't really understand why I would want to use this atomic fence. Instead of using more correct ordering in the compare exchange, right? This is saying that they're using relaxed ordering here. They don't really care about something. But then they use a fence that says we're acquiring here. This might be like a minor optimization. Or it might mean that there's like other reorders that might be a problem. I'm not sure. But I was more concerned when I didn't realize they were saying relax here. So I'm not really going to think about it. And we'll just keep in mind that, so hold on, let me finish my thoughts. So if we look at like the definition of release and acquire ordering, I think I saw somewhere that all memory operations that happen before the acquire and release will happen before. Here, visible side effects. Well, hold on. If side effect A is visible, blah, blah, blah. Where did I see this? Here we go. Atomic operations tagged as this will not only order memory the same way as release acquire ordering. Everything that happened before store in one thread becomes visible side effect in the thread that did a load. Here. This is where I saw. So this is saying that release acquire ordering ensures that everything that happens before store in one thread becomes a visible side effect in the thread that did the load. Perfect. And so what I was concerned about is that without a memory fence, without like a explicit fence, I wasn't sure if that was true because like I saw them doing that in their fence docs in the Rust docs. But I mean, that's because they were using relaxed ordering on a compare exchange. And I don't really fully understand why you would do that. Unless it's like, maybe it's faster to do the one fence after with relaxed comparisons in the compare exchange. Not sure. But we'll kind of ignore that for now. So let's run right now just to make sure that nothing's going crazy. It does seem like things are working fine. It's kind of hard to test this, so we're going to keep an eye out for synchronization issues. But for now, I think that we can say that our mutex is fixed. And that's at around 19 minutes in. Okay, so let's start looking through other implementations of other places where we've said that we're sync, where we're not, and kind of see what that looks like. So, unsafe impl, or let's just say sync for. Okay. So we have this spin lock type, which has this is using atomic, so that's fine. Our async mutex we already checked. Our lock free queue, where we implemented last stream, we're pretty just good. Our interrupt guarded. So this assumes a single threaded OS, and this is really scary. So let's look at uses of interrupt guarded. Okay, so what is this guy doing? Maybe I'll open up a little paint. So what happens is our OS is like running some code, right? We've got like code, and we're like here. And then all of a sudden, something happens on our system. Like maybe an Ethernet packet comes in, and we need to we need to service that. And so what happens is when we get an Ethernet packet in, an interrupt from the Ethernet card triggers and says like, "Hey CPU, you got to check what I just did." And what'll happen is we'll actually like after every instruction we go like check the interrupt line and we go, "Oh, it's time to do some other work." And so we'll like jump over here to this other section of code. And we'll go like from here and we'll go do 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 do, and we'll like run the code that's in here and then do 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 come back. Now the problem there is if you assume that if you want to like synchronize something between these things, like have some static memory that both can read and write to, you need to make sure that like you're not modifying shit in here when you jump out. And so the way we've been doing that is we've been using an interrupt guard to say like, hey, this thing in static memory is like totally safe to use by everyone. Now the problem with that is if we have like this thing in static memory over here, sure, like if we previously cut these lines and say don't interrupt, sure, only one of this guy can be accessing this, or he's done and only this guy will access him. Great. But what happens if we have like another CPU executing code over here? He's here and he's also trying to access this. All of a sudden, disabling interrupts isn't enough to prevent multiple people from reading and writing this guy. And so this is like an invalid implementation of sync. So what we should do is we should look at who's using this thing and try to figure out if they are safe or not safe, you know? And I think probably the real answer is like the vast majority of people who are using this as a synchronization mechanism are invalid. So let's start looking at those. So our sleep implementation is using it. I'm pretty sure this is not safe. This is no longer good. Let me think. Thinking. Yeah, this seems bad. So the design here was, how do I draw this? We have like this RTC, and what he does is every time he's got like a little rock in him, and there's like electricity running through this guy, and basically every time he pulses, he's gonna fire an interrupt on the CPU. And this might trigger, if we had like some code that was like sleeping, we might ask for, say we wanted to sleep for 10 seconds. We convert that into like a number of times this interrupt will fire. And we say like, hey, when you see like the 50th one of these, wake me up. And so we have this like wake up list that happens that like keeps track of all of these. And so when we like start a sleep, we register a time that we want to wake up at, and then the interrupt handler will check, we'll call this like wake up if necessary, and wake us up if it needs to. Now, if we want this register wake up time, these like wake ups to be visible from multiple threads, or sorry, to be like, if we want to be able to sleep on multiple threads, we're going to have to like register wake up times for each of them. And let me think about this. You could have like one wake up list per CPU. But then if we start reordering things around, that'll be a problem. Like if we start like moving work from one CPU to another. So probably what we need is like one list of wake up times that's writable from all threads and only readable from the interrupt handler. Which starts to sound like like an interrupt queue, kind of. Or sorry, yeah, like a queue of some sort. So let me think. How do I want to handle this? So, what we have right now is like a set of all interrupts or all wake ups times. And what we want is we still want to maintain that list. We just want to make sure that only one thread is modifying at a time. And we need the additional guarantee that the reading these will never be blocked in the interrupts. So maybe what makes sense here, an interrupt guard is still like maybe reasonable here, right? Because like if we tried to like make a queue, or we tried to convert this into like a queue, hold on, you could say that like your interrupt handler runs over here, interrupt handler, and he could keep track of the list of wake up times with a set, hash set. And he has like a channel that he like receives requests from, so like an RX. And we could have like all of our different threads with our like little TXs. And they could all write over here. And then the interrupt handler could like pull from these and stick them in his like internal set of values. But the problem with that, I think, is that we don't know how to say this. If this interrupt handler doesn't run frequently enough, then we could like run out of room on this queue, right? If this is a queue of like 4, 1, 2, 3, 4, and we like push like 10 wake up times to this guy before he runs, that's gonna be a problem. And so I'm trying to think if it makes more sense for each thread. Sorry, the other constraint here is that my lock-free queue doesn't have any like resizing. So we can only preset the size of the queue, and if we run out of room, then it's like game over. And so maybe what makes more sense is if we could somehow manage this set on like the non-interrupt side and only look at the set from the interrupt side. And so maybe it makes sense to have something like let's see, maybe it makes more sense to have something like keep this like an interrupt guarded hash set. Then maybe from multiple threads, we could try to modify him somehow. Like if this was like mutex guarded in how do I say this? You could have like visible wake up times is an interrupt guarded hash set. And we could kind of make the guarantee that this will only be accessed from single thread plus the interrupt handler. Right? The idea being that like this is only synchronized with the interrupt handler, but not with multiple threads. And then you could have something like a mutex guarded queue of times, and like whichever thread owns the wake up list, maybe he like tries to move these from the wake up times to the visible wake up times. Sorry, he like moves them from like multi-thread mutex context into interrupt handler visible context. And I'm trying to decide if that makes sense. So if we push like 50 of these wake up times in a row, this would like realloc fine, right? We don't have to worry about like lock-free reallocation because we have like mutexes. And then we have like 50, and then we have to push those to the interrupt context, and we would be able to like inject those all at once, and that's also fine. We would disable interrupts when we move them over. And the question is, does that make sense? So what would that API look like? Here you would have like you'd have like a service function that is the mutable reference to self, right? To say I'm the only person who is using this. And he does something. He like iterates the wake up times and he pushes them. So he says like self visible wake up times dot insert wake up time, and then he clears the other one. So he says like self wake up times clear. Hold on, I'm just realizing now that I forgot to checkpoint. So let's make sure that I commit the atomic fixes for the mutex first before I start breaking everything. Sorry, I should say async mutex now thread safe. Okay. So sure, we have like a service function. He gets called every once in a while. He like reads all of the values that other threads try to push, and he sticks them into the ones visible to the interrupt handler. And now the question is like, how do we have this set that's visible to the interrupt handler? Well, we like disable interrupts while it's running. Great. That seems reasonable to me. So then what will happen is the interrupt handler will have a handle to this, which seems reasonable. And it would be nice if we could like maybe enforce somehow that this is only called from the interrupt handler, right? Like the idea is that in our interrupt, our like interrupt guarded is a semi-valid synchronization primitive, but only in the context where we're synchronizing with an interrupt handler and with no one else. So maybe what we do is we split this wake up list into a portion that we feed to our interrupt handler and a portion that's used from our like multi-threaded normal code. That seems reasonable. And then we move this like wake up if necessary into that, and then it's like hard to accidentally use the unsafely guarded thing from the wrong context. I think that makes sense. Heyo, what's up? So maybe we say it would be nice also if like the interrupt handler had a way to that you could like we could like abuse the type system to make sure that there are some things that can only be called from the interrupt handler, right? If you took in a type here that said like key comes from like interrupt handler key, you could maybe like say that the interrupt handler key is, oh, the title says lock free, but the mutex is right there. I've been bamboozled. Sorry, I forgot to update the title today. Hold on, let's just fix that. You're right. That was last stream. I apologize. So let's change the title to preparation for multi-core in my Rust operating system. Did it work out? Yeah, we we're working on it last stream, and we got to a bit of a problem where we were struggling to like finish. Like we finished the queue, but we were having trouble with like initialization, and there was just like a minor Stack Overflow problem that we hit at that point. But yeah, we have a lock-free queue now here. Let's see if we can find it. So we do have a lock-free queue. He's got like a sender that uses atomics and a receiver. They use atomics to like synchronize. And then our logger, he's got the lock-free queue sender and receiver. He does have like a mutex around the receiver because we've kind of made the rule that our we've got like a multiple sender, single receiver. And so our single receiver needs to make sure that he's the only one accessing it. So we still have a mutex around that side. But from our interrupts, we do push these. We like go into our interrupt handler and we can push logs to this like lock-free queue without having to block or anything, which is pretty cool. Pretty cool. What we're working on now is we are now trying to evaluate like the other places where we were using interrupt guards as like a synchronization primitive, and that's kind of illegal if we start actually having multiple cores. Right now we have one core of execution. Why not new type the receiver and make it uncopyable, unclonable? Because the logger class is going to be available for multiple threads, and so you need to make sure that like the internal to the logger, only one person is doing like the looking at the receiver at a time. You could like instead extract the receiver and stick him in his own type somewhere, and you could, if the receiver was uncopyable and unclonable, then you could like handle that service somewhere else. But it made more sense to me in my head to have like the logger on everything. Shouldn't the logger that each thread uses just be center? Yeah, that's definitely like a valid. That's a valid way to think about it as well. But the way I did it was that I had my service loop is like inside the logger. But you're right. Maybe this should live somewhere else. Sorry. Yeah. So what are we on now? We're trying to fix this wake up list. So we have this interrupt handler that runs. He sees that someone has tried to, like a thread has tried to sleep. We check our monotonic clock on every interrupt, and we see, oh, we've hit a time where it's time for someone to do some work again. And we're trying to figure out how to manage that where multiple threads can set wake up times, but the interrupt handler can view them without blocking. Okay, so I was thinking that we have this like wake up time thing where like multiple threads can post to the list and say that they want to wake up at a specific time. Then maybe on a service loop, we like convert those into something that can be viewed from the interrupt handler. Great. That seems maybe reasonable. What kind of OS is this going to be? There's no real like end vision in mind. We're just kind of trying to see. I think we're just gonna see where it goes. I probably will eventually have some form of user space, but I don't really think I'm gonna like commit to any particular type now. All I'm trying to do right now is see like, what if I want to do stuff on an x86 PC? Like, what I want to send some network bytes. I want to make a web server. I want to write a game. I just want to see what all of that kind of looks like to build an intuition about what's actually happening on a real computer, on a real operating system. Okay. Focus time. I'm going to go back to trying to fix this wake up list. So, right. I was going to say that in the interrupt handler, there's this like interrupt context and the wake up context. Great. So the interrupt guarded, I think all this is fine. So let's just start trying to punch through this like, actually getting this to compile with what I've stubbed out here. So here we have my util async mutex mutex here. We need to pull in the vec deque from alloc. So this is vec collections, I think. Vec deque. So here we create a wake up list, and we have wake up. This is like posted wake up times maybe, and interrupt visible wake up times. I think is probably a okay way to think about this. Having this guy as a one class doesn't make sense. Actually, we should have we need like the two ends. One that's going to be visible from multiple threads in non-interrupt context. So we'll say we'll just call that the wake up list. I don't know, we'll think about it. This is going to have a mutex vec deque inside, and he's actually going to have an arc mutex probably, right? Because there's going to be multiple people that have handles of this maybe. Nah, there's just going to be one of them. So then we're going to have the like interrupt side. So let's think about that. Oh, there are going to be multiple people for this. Sorry. Thinking. We're going to have, I think there's going to be three things here. There's going to be the like poster side, which has only immutable references. So this is where multiple threads will use this to request sleeps. Then there's going to be the service side, who has a mute self. And he's going to take post requested sleep times and move them into interrupt context. Sure. And then we're going to have the interrupt side, which views the interrupt guarded set. Great. So what are each of these going to be called? This is going to be called like wake up request, requester maybe. This is going to be the wake up handler, I guess. And this is going to be the wake up handler interrupt side or something. I don't know. We'll figure it out. These names are subject to change. So here we have wake up requester. And he's got this like queue of wake up times that he's pushing to. And I guess this needs to be an arc mutex because we know that he's going to be looked at in both of these guys, which means that we need a shared reference, which is an arc, an atomic shared reference. So here I think we have sync arc is where this comes from. Nice. And he's going to have this register wake up time that we had before on the old version. But he's going to do this. Posted wake up times log, posted times push. This needs to be an async thing now because our mutexes are async. And I think this needs to be pushed back now. Great. Great. And now we have this like wake up handler, which is the guy who moves him from one context to another. So he's going to have the queue of times requested from other threads, as well as this like interrupt guarded thing, which is, and all he's going to do is he's going to have a impl wake up handler who has a function service. And he basically just migrates from one to the other. So he's going to say let wake up times equal to self posted wake up times lock.await. He's going to say for time in wake up times I think there's like a drain function in wake up. Oh, I've got an extra E in here, that's why. Wake up times drain. Which will like take values out of the vec DQ and give them to me. And in here, I'm just gonna say let interrupt times is equal to self dot interrupt visible wake up times dot lock. So this disables interrupts. This disables other threads from blocking me. And then here I say interrupt visible interrupt times dot push or insert. There we go. Time. Great. This needs to be mutable. Great. And then we have the interrupt side, which only has this guy. So we have the pub struct inter. Maybe we just give the wake up handler to him as well. No, we can't. Shit. Okay. So we'll say wake up list or wake up list interrupts or something. So this is the side that's going to see the interrupts, the wake up times in the interrupt handler. And so in here, we need this wake up if necessary function. Great. Impl wake up list interrupts handler. That seems more reasonable. I don't know. We'll see. I don't really like this name. That's fine. So here he looks at the wake up times. And that's it. He's done. Okay. So now we delete this previous wake up list shit, and we need to figure out like how we construct these guys now. So what do we do here? We say pub function get wake up handlers or construct wake up handlers. And he's actually going to return all three. Wake up requester, wake up handler, wake up list interrupt handler. These are bad names. And so he's gonna first construct the wake up time. So he's gonna say let posted wake up times is equal to arc new mutex new vec dq new. I guess that's it. These guys also have to be arcs now, because it's visible from multiple contexts. How was I handling this before? Before I must have had one reference to the list that was being passed around. Oh, maybe I externally had... That's what it was. I externally stuck it in an arc. But now that's a little less possible. Okay. So in here, what do we do? First of all, I've got mismatched brackets. Oops. And here we need to make the interrupt visible wake up times. Interrupt visible wake up times. It's going to be an arc new. Interrupt guarded new. Hash set new. There we go. This guy fronts and brackets. Great. And then we say requester is a wake up requester. And what does he have? He has posted wake up times, which is an arc clone of the posted wake up times. Great. Then we have the handler is equal to a wake up handler. And he has the posted wake up times as well as the interrupt visible wake up times, which is a arc clone of interrupt visible wake up times. Great. And then we have the interrupt handler is a wake up list interrupt handler that has the interrupt visible wake up times. Like this. And then I guess we return them all. So we have requester, handler, wake up, interrupt handler. Does this make sense? This feels a little convoluted. But this does allow us to ensure that there's all, like, we don't have to worry about synchronization here, which is good. So maybe we'll drop some comments on here probably. So then in our main, previously, let's think. We had this wake up list, but now we're gonna have to have several. Let's actually sort out the names before they start spilling out everywhere. So let's look at sleep. And what do we want to call these? Wake up requester seems reasonable. Wake up list does not seem reasonable. Oh, wake up list doesn't even exist, so great. That's good because it wasn't a reasonable name. So wake up requester. Multi-thread way to request wake ups. We have the wake up handler, which is puts or registers wake up requests with interrupt handler. And here, this guy runs wake ups in interrupt handler. Or checks wake ups in interrupt handler. Now, maybe it makes sense. Maybe we could like prevent this guy from leaking out. Maybe if we like pass in an interrupt handler, or like our interrupt registry, we could register this with the interrupt handler in here. But I guess this guy doesn't know about the clock and shit. This isn't really a handler, right? This is like an interrupt. A wake up list is like meant to be used from the interrupt handler. So we'll say like interrupt wake up list. Sure. And this is like wake up propagator or something. I don't know. These are all gross. This is all disgusting. I don't like names. But that's fine. So our sleep feature will take up a wake up requester now. That's who most people should use. Great. This is also a wake up requester. So now in our kernel, we have wake up requester. Oh shit! I already forgot the order. We have wake up requester, wake up service. We'll call it, maybe makes more sense, and wake up interrupt or interrupt wake ups. Sure, is equal to sleep construct wake up handlers. So here I'm okay with calling this wake up service. I like that name better. Here on tick, this is the interrupt handler function. So we'll say here we take the interrupt wake ups and we wake up if necessary with the tick, right? That's one thing out of the way. We don't have to keep track of that. We do have to keep track of the wake up requester and the wake up service. Great. And so here we just package in the wake up requester and the wake up service. Great. And now everywhere where we used wake up list before, we used wake up requester. Great. We're getting close. We are getting close. So here we have wake up requester and wake up service. I think those were already included here, are they not? Here. Great. And this guy goes away. I think that's most of it. Cargo check, let's take a look. In our game, we tried to use the wake up list, so we'll call this wake up requester. Okay. Cool. Cargo check. Who else is using him? TCP used him for... I think that this was a way to get us to time out. In some cases. So here we have wake up list, and this should be wake up requester. Great. Cargo check. We have him as like reference counted wake up requesters all over the place, and we actually don't need that anymore because internally he's already reference counted, so we'll just derive clone here. And everywhere we see RC wake up requester, we'll just replace the wake up requester itself. Great. So let's look up RC wake up. RC, maybe I need to escape that? Nope. Alright, cool. Whatever. I don't know. This is an RC clone that we don't need. We'll just say here clone. Okay, is that good? Cargo check. Here we have an RC clone at line 562. And all right, we will. What is this even for? Oh, this is like a sleep function that we're sure. Yeah, okay. Cool. Actually, I think I don't need this anymore. Cargo check. Okay, so we compile. There's some awaits that need to be stuck in places now because there was like an async mutex that's in use. So in here, 92, this guy needs an await on him. Which is annoying. So this is an async. Shit. Okay, so we have. Sorry. Let's think about this. So he has this feature that pulls the monotonic time. Great. On new, we need to register the wake up time, but that also needs to be async. So is this really gonna be async function new? That he needs to await this, and now I need to double await? That doesn't seem nice to use at all. That's stupid. Definitely stupid. Maybe what we do instead is we check. Maybe we have like a bool in here that says if we've registered already. And no, that's not great. We'll just make it an async function for now, I guess. However disgusting that looks. And we'll just double await it. Gross. Does anyone else use this? No, so maybe I just don't make this public, and that hides the grossness. All right. Nobody ever uses the wake up service, so in our demo, one of the things that we need to do is we need to service the wake up handler. So in our demo, is this the right place? Maybe this needs to be all the way out here, actually. Yeah, here, we'll put it here. We'll say kernel dot let's think about this. We'll say let yeah, I guess he does go in the demo. He will. So here we'll just say one of the many things that you're going to do is you're going to self wake up service. Cargo check. We need to pin him, which basically says like, hey, don't let me move, please, so that my memory stays valid. And let's kind of run and see if our thing is still working. So here we can tell it's already fucked, right? The fact that we're not waking up here, this is like the frames aren't moving. That indicates that the sleeps aren't working correctly anymore. So we've done something terribly wrong. And I wonder how we can check that. So I guess here, the problem is that in our, on the interrupt handler side, we're probably only waking up if we saw that exact tick. But in this case, we might have actually already passed it. Because now there's like a little bit of delay before it gets into the interrupt handler. So wake up if necessary here. We can say, what do we want to do? We kind of want to like iterate over the times and pop the ones that are have passed. So we almost want to say like first of all, we kind of want these to be sorted. So maybe like a hash set here doesn't make sense anymore. Before we could guarantee that every single tick was going to be hit. But now we can't guarantee that. So let's look at this type. This is before was an interrupt guarded hash set. And now maybe we just say BTreeSet. If we have a BTreeSet, then we can guarantee they're in sorted order. I think. Let's look at the BTreeSet. Ordered set based on a B-tree. Very nice. And so now we can iterate over items in our set. Right, so here we can say while... So we can say for item in self.wakeup times. We want to enumerate this probably so that we can get the index. Sorry, this should be wake up times iter enumerate. So then we have I and the item. This should be time, actually. And we'll say if Oh, this is the item, sorry. If the item is less than time, if the item is greater than time, break. The idea here is that we're iterating over items until we would have to sleep to get them, right? So here if we have like 0, 5, 15, 24, 32, or sorry, 16, 34, and the input time is like 10, we want to basically say like C 0 and 5. And if 0 and 5 weren't here and we got 10, we would want to do nothing, right? So here, we're basically trying to say, if the item is bigger than time, so 16 is bigger than 10, break. Now, we'll say last index is equal to 0. And here we set last index is equal to I. So the idea here is that we keep track of how far into this list we make it. And if last index is greater than, say, if last index is greater than I, is greater than 0, we wake up the executor. And we should probably delete everything up until the last index. So here we should say wake up for I and 0 to last IDX. No. We say we go through each of the wake up times in order. But we only take the first n. So like all the ones that came before all the ones that came before. We remove them. So for item in this, we say wake up times remove item. Great. This needs to be mutable now. And I think that there's probably a bug in here. Because in the 0 case, we set last IDX to 0, even if the 0th one was to be removed. So maybe we do I plus 1. And then I think the rest works. Right, so take 1 if would be for the first 0 at the index. Great. And let's try that. So we'll cargo run. Why did something change now? Oh, because we used a hash set here instead of a BTreeSet. And anywhere here, we need to change this to a BTreeSet as well. Great, 63, oopsies. Here, we try to remove stuff. That's annoying. So we actually have to like walk over these guys. Oh, that's annoying. Let's do it this way, actually. So when we go over these guys, we keep a list of all the times that we have to remove. Unless there's an API on the BTreeSet to like delete the first n. Is there like a partition, remove? We can remove specific values. Can we get like, what's the last? This is the last item. Is there like, I don't see anything to be like delete the first 5 numbers. Which seems reasonable. Like it's kind of, oh, we have pop first. So we can just do that. For I in wake up time 0 to last IDX, wake up times pop first. Great. Great. That is what I want. Where first would be the lowest number. Minimum element in the set. Great. Okay, we're still not moving. So maybe it's time to start printing some stuff. print line. So we're going to print the time and the wake up times. Like this. And wake up times cannot be formatted like that. Oh, probably we need to dereference him. So here it says that there's no wake up times. That's interesting. So maybe this like service loop isn't being run. Okay. Finished servicing. Ah. Okay, so that's interesting. So he never gets a posted wake up time. So that's interesting. Why not? Oh, because he just nope, not seeing it. Let's see this again. So does he ever make it here? Or here? Yeah, he does. Is it possible that this isn't valid? Okay. So he does get times, but he never finishes. So is it possible that like this drain isn't valid? Removes the specified range from the DQ in bulk, returning all removed elements as an iterator. If the iterator is dropped before being fully consumed, it drops the remaining removed elements. Or if the endpoint is greater than like the DQ. Oh, oops. So this should be wake up times len. So it's an invalid iterator. So say let len is equal to wake up times len. Here we pass in len. I don't understand why this never finishes. That's very odd. There's definitely something fucked going on here. I'll be the first to say it. We'll print here registering to try to get a feel. So two people register, we service, we get the two numbers. And then like, why do we never exit the loop? Like, shouldn't here, why, like, we get the two values, we print them, or got time here. Interesting. So probably it looks like we disable the interrupts, and then just get like stuck. It's very odd. So I do see a problem here where this is supposed to probably loop. And kick itself out of here. It's supposed to like wait for new times. So we'll call this like time waiter. And he takes in the self.posted wake up times. And he awaits. So that's one problem. Now we need to, because like what was happening there is he's supposed to forever wait for new times to come in, and when they come in, then push them into the interrupt visible queue. And he was only doing it once. Now that I doubt that's a problem, but I want to fix that here anyways. So here we could say struct time waiter, and this guy is related to the wake up service, and he takes in the wake up times. wake up times. And he takes in, like, that's a reference to a arc mutex vec deq usize. Let me double check if this happens before our allocator comes up. That would be a problem. Nope, this comes way after our allocator, so that's good. We're allowed to use the heap here. This guy needs a lifetime on him. And we need to implement core future for this guy. And here he needs to implement, for time waiter. For any lifetime, we need to implement the poll thing here. His output is going to be nothing. And here we say let times is equal to self posted wake up times poll. Probably. This guy doesn't like that he's missing some types here, so this guy needs to take in task poll, pin, task context probably. Great. I spelled wake up wrong here again. Somehow I keep doing that. He needs to be pinned, so let pinned is core pin self posted wake up times. There we go. He doesn't like that actually. Oh, this is lock. Right, like this. Here he pulls the lock to get the times. We check if the if this is locked. So if we say there should be a match here, let the times is equal to match pin poll. That's the X. Great. You can await a struct constructor. That's how you're awaiting the struct, which is the feature, not the constructor. Yeah, sorry, that wasn't clear. Yeah, I'm like trying to like make this guy in one shot and then wait for him to finish. So here, if he is poll ready value, we get the value. Otherwise, if it's pending, we return pending. So now here we have like a list of the times. This is like a mutex guard of the queue. And we just say if times is not empty, is basically. If he's empty, we return poll pending. Else we return poll ready. So the idea here is that we are looking at like all of the times that we have. And we're trying to say like, if there are any in there, then we're ready to continue this loop. Otherwise, do something later, do something else. All right. Dude, I don't know how I'm fucking up the spelling of wake up this bad every time. My fingers just aren't getting it. Okay. Let's try cargo running here. I don't expect this to behave any better. Definitely not. So, but maybe, okay, how can I try to bisect this? So, we have this got time, inserted time, and here he's never inserting the second one somehow. Do I have some sort of fancy keyboard? No, why? So this insert is actually failing somehow. That's very odd. So this interrupt times is a type of interrupt guard BTreeSet. So here my interrupt should be disabled. I should just be inserting into a normal BTreeSet. And That's really odd. It's possible that the BTreeSet is not behaving the way I expect somehow, because maybe my allocator's fucking busted. That seems like very possible. Very, very possible. So I wonder if there's a way to check that in some way. So what is the thing that's happening? I'm like halting. I'm like fucking up so bad the CPU's halting. Bailout. Assertion failed. You're typing so fast, I've only ever seen people with fancy ergonomics keyboard get that fast or something coding. Oh, yeah. Probably what you're seeing is like, I've typed a lot, so, I spent a lot of time on it when I was like younger. Yeah, no, it's just a normal keyboard. It is like a mechanical keyboard, but I don't really think I type any faster on these than I do on like my normal laptop keyboard or anything. It's pretty normal. I just would play Type Racer with my friends, and just I was very competitive, so I grinded like Neopets typing game. I played this so much. I wonder if it still exists. Typing Terror from Neopets. Oh yeah, I played this game all the time. I just played this for like years. I wonder if it's still... Oh, this is bringing back memories. 2023? How long? Neopets is still going? That's crazy. Well, I guess it's... Oh, this is Neopets. Wow. Oh, I'm not logged in. They won't let me play. Fuck. Well, hey, it's running Ruffle. Yeah, that's pretty cool. Anyways, yeah, I played a lot of typing games. Oh, you're saying but for normal words, not for code? Well, I've written a lot more code in my life than I have real words, probably. There's also like, I've got like auto-completion a little bit, so like, that helps. Okay, so my BTreeSet is fucked. How can I try to like bisect this a little bit? When I'm inserting this, it's just like crashing my CPU instead of doing something sane. So the obvious like list of problems is that I must be like, for the CPU to be crashing, I must be accessing memory somewhere that's illegal, right? Like either I'm like corrupting my code by like writing to somewhere that I'm not allowed. Like if I'm like executing code and then I overwrite that code by mistake, and then it tries to execute just like a random number, that could cause a CPU assertion in QEMU. Or maybe like our permissions handling for like which areas of code are writable, maybe that's not working correctly. So let's go to our interrupt handler and try to print out like so what could happen is if we like segfault, we like access some invalid memory, maybe this like interrupt handler is triggering and that's causing problems. So can we print line in here, received interrupt number, and let's see if that's happening. So I don't see any like interrupt numbers happening, which is interesting. I wonder if there's a way to trigger this intentionally just to make sure that that log should print. Like if I just try to like dereference 0 somewhere. Like here, I just say like 0 as U8 dereference. Does that trigger an interrupt? No, that's fucking crazy. Maybe because I don't ever do anything with it. Okay. That's interesting. I see for pointer null as a U8. Shouldn't this cause like something immediately really shitty happen? I would think, but I guess so that's a clue that like just dereferencing random memory isn't going to cause problems. What if I try to write to it? So we can say write, I guess null mute is what I need here. And if I try to write like a 0 to this, does that crash? No. Okay, so we have like no memory protection at all. So that's an indication that we wouldn't even see an interrupt there if we wanted to. So that's interesting, and probably something to look into at some point. Maybe what we can do is, instead of running our doing this in the wake up stuff, maybe we can kind of like disable a lot of our demo here and just see what happens if I try to like construct a BTreeSet. So core collection, core, or it's alloc, I think, collections, BTreeSet, new. And if I just like drop a couple usas in here, like, I don't know, will this cause the same type of crash? Why received interrupts 72 wake up times? So this doesn't look good. Like, why am I not seeing this print line? I'm also surprised that I'm seeing any sleeps at all anywhere. So that's kind of weird. Oh, here I am running the sleep down here. So let's see. Why am I seeing that? Time 1 week. Oh, because, no, I don't understand. Oh, because I'm calling wake up if necessary if I see the, interrupt. Oh, I wonder if it's something to do with, like, popping stuff from the wake up times. I wonder if I'm, like, corrupting memory and this interrupt guard isn't guarding like I think it should. That would do it. So let's try disabling the interrupt handler stuff entirely and going back here and printing stuff out. If there was some sort of memory corruption because of that, that would make sense. Let's print something here. Hello world. Interesting. So it looks like just using a BTreeSet is like crashing my machine in some way, which kind of indicates that the allocator is doing something wrong. Right? That's what it sounds like to me. Like, with all of this stuff off, just using a BTreeSet seems to be causing issues. So I only get through 2 pushes to a BTreeSet. What if I don't run in release mode? Still, okay. Okay, this is really, we're getting somewhere. So if I go into my memory allocator and just start logging allocations, maybe this will give me a clue. So let's say print line here. We're going to print the location of memory that we allocated, as well as its size, maybe. So we'll say let size equal to header pointer dot size. And here we say we put the header pointer and size. Like this. If I run this, so shouldn't I be seeing, why am I not seeing any of these hello worlds anymore? Cargo, run, release. We die halfway through this print? What the fuck? That's interesting. So these are 8-byte allocations. So it could be that there's a problem with our usage of 8-byte. Like our 8-byte allocations could be broken. Oh, am I remembering something about like our allocator overhead was maybe causing problems here? I guess here we might also want to say allocation failed. Let's just try, make sure that we're not hitting this like allocation failed state. This is weird too. The fact that we're getting like stuck in this like 8-byte allocation loop, it's like why? Right? It looks like we're trying to allocate in our B tree set like one item, and that's just like for some reason looping, which is pretty weird. Maybe we can print out what the what the layout is. Right, like what are they asking for and why is it behaving this way? So they are just asking for a bunch of 8-byte allocations. And I wonder why that's not, it wouldn't shock me if 8-byte allocations are triggering some bug in our allocator that we didn't notice before. Can you trace the origin of those allocations? I don't know. I don't think we have any backtracing abilities right now. At some point I had GDB working, but it stopped working, and so that makes like I didn't bother adding any like backtracing ability at that point because GDB was good enough. But now that GDB is failing me, this is starting to get like this. It might be worth taking a break, setting up GDB, and coming back at this tomorrow with fresh eyes. But I would like to like just poke a little bit harder first just to see if I can like debug it without it. But you're right, tracing the origin of those allocations would be nice. It must be from within the B. I'm like positive it's from within the B tree set, and we could probably look in here and see what it's doing. So this is a B tree map. The B tree set is just a fancy B tree map. And where does he allocate? Somewhere in here. We probably like push an entry somewhere. And what's the like API for allocators again? It's like, I think it's just an alloc, yeah. Alloc with layout. So here, can we look for like layout? This is, since he's using a B-tree map internally, the allocations are probably coming from here, and he must be calling alloc somewhere, so maybe not clear. He's got like a bunch of, he's passing the allocator around. I don't see him doing the reallocations though, which is annoying. I would have been cool to see. Oh well. I guess I'll try GDB really quick in case it like maybe it fixed itself. So in here, I think we can go, what do we do here? We say, we look at our wrapper script and we tell it, when you start QEMU, stop doing anything and wait for a GDB connection. And then here, I think I initialize my shell and I think I call like GDB on target debug kernel, and I say target remote localhost 1234. And then I think I can like set a breakpoint at my allocator, and let's just see if this actually does anything. So, well, let's go into main actually and look at our BTreeSet and just break at this line. So I think I have it continue. Okay, wait, so this seems like it like might actually be working. So we got one hello world printed, and we see a set insert. Great. And I said next, next, next. Oh, okay, that doesn't seem to be working quite right, but I think breakpoints might be working okay. So maybe here I can restart this. And I can break on this again. And say target remote localhost. I can continue. That doesn't look like it worked right. Target remote localhost. Kill, shit, one more time, one more. Target remote localhost. I think I maybe have to restart GDB. Then in here, I say target remote localhost 1234. I try to break on this, line 286. And then I continue. No, something... Oh, it's actually dying before that hello world is ever printed now, which is kind of interesting. Kind of interesting. Let's try to make sure that that other BTreeSet isn't being used at all. So I think that was like wake up service. Yeah, nobody's running that. And then in our sleep, we want to make sure that the interrupt handler isn't accessing them either. Great. So really nobody should be using this BTreeSet anymore. Let's try to like delete as much as we can from here so that like nothing else is happening. And here we'll cargo run. This is recompiled, so we have to reinitialize, reload the file. We connect to the localhost, and where were we trying to breakpoint on this like BTreeSet stuff? So we break here and hit continue. Okay, there we go. There we go. We're at the spot we want to be. And now what we want to do is we want to go into the allocator and try to backtrace where these logs are coming from, where these layouts are coming from. So we're going to break a point here, continue, backtrace. Oh, here we go. Hey, wait. But GP's actually being my friend today. Last time I tried this, I was struggling. Okay, so here we are in fact trying to allocate from within the BTree map, which is fun. So here we go. So this is a 52 size thing. And this is no longer looks like we're failing because of like the small allocations. It looks like we're still struggling for another reason. I think just for sanity, I'm going to try to disable interrupts here. Just in case that's related in some way. I doubt it is, but I want to know. So here we can say guard is equal interrupt guarded new this, and we say let guard is equal to guard.lock. Okay. So for the duration of this, we should have no interrupts. Here we need to reload the kernel. So we say file kernel, yes. Yes, reload. And reconnect to the target. So target remote localhost 134. And now we're gonna breakpoint here. We want to delete that breakpoint, and we're going to continue. Okay. My brain's fried. This is a problem, though. And it's interesting that we might have accidentally found a bug in our allocator just by using a BTreeSet. So I think I'm going to call this here for today. And what we're going to do is tomorrow we'll come back and we'll try to like really sit down and think about why, like what could be wrong with our allocator. I'm going to have to like brush up a little bit because it's been a month or so since I implemented it. But yeah, this is going to be fun. So thanks for watching. Apologize for like the scattered brain on this one. I didn't really think that we were going to be hitting this type of problem here. But if you like what you saw, you can tune back in tomorrow and we'll keep debugging. I'll probably be on around like 1:30 or 2 Pacific time. Or if you like what you see and you're not around to watch live, you can always catch up on YouTube. YouTube is linked in the Twitch description. And if you're watching on YouTube and you want to check me out live, yeah, streaming most days at like 1:30 or 2 Pacific, feel free to drop in. Twitch link is in the YouTube description. Thanks for watching. Catch you on the next one. Bye!